minute late, but we'll be okay. Jerry, we'll call you on time. So the people I don't see are Amanda, Alexis, Chad, Austin, Edward, and James. No objections? Okay. Since Darla's still in here, I'll do something other than going on with the lecture, if you'd listen. Michael asked about a question on the test that he'd really love to see an answer for. And that question was the one about the marble dropped in the satellite. And so the question says that you have the Earth with the satellite orbiting the Earth at H, where H was 200 kilometers above the surface of the Earth. And inside of that satellite, a marble is dropped. Then it asks what acceleration is seen for that marble as viewed from Earth. Now, if you were inside of that satellite and you dropped the marble, what would you see? What would it do? It would float. Now, it does not float because there's no gravity there. Why does it float? It's in free fall, and you are too. And so the two of you are falling together. And the question here is, what's the acceleration at which both of you are falling? They put it in terms of the marble. Remember, I don't write these. They put it in terms of the marble so that you would think about that object instead of, put it in it's a satellite and does this. So I have that marble in the satellite, but it's doing the same thing the satellite is. It's falling toward the Earth. Now, if the satellite's going in a circular path, what would we call the acceleration? We'd call it the centripetal acceleration because it's the acceleration toward the center necessary to keep it going in a circle. So if we knew things like the speed and the radius, we could get the centripetal acceleration, right? Because we know centripetal acceleration is v squared over r. But we don't know the speed. We only know the radius part of that equation. So we have to go to plan B. Yes, Diksha?
So the radius, when you say we know it, is it just that 200 kilometers, or is it the radius?
It's the radius from center to center. Okay. So it would be not the 200 kilometers, but that plus the radius of the Earth. Okay, so we have to go to plan B, and plan B is, what's making it accelerate? What's your answer to what's making it accelerate? Gravity. So if it's gravity making it accelerate, I just have to use Newton's second law. So my concept is going to be use Newton's second law to find acceleration. So to get that, I say, what forces are acting on my marble? That force would be only one force, force of gravity. And the force of gravity has an equation. Fg is equal to capital G, mass of the Earth, mass of the marble, divided by, and I will put d squared, whereas Diksha clarified, d is equal to the radius of the Earth plus the height above the surface of the Earth. So that's my force. Newton's second law says sum of the forces. I still put toward the center. I'm just going to find that centripetal acceleration from Newton's second law. And so then my work, so here's my equations. And my work, changing to, green's a good work color. Sum of the forces is force of gravity, G, mass of the Earth, mass of the marble, divided by d squared is equal to mass of the marble, AC. If I just divide both sides by the mass of the marble, I have my answer. The acceleration is equal to capital G, mass of the Earth, over that d squared, where d was the radius of the Earth plus, I don't know why height didn't stay there, but plus height. And so if you put in your numbers, which I'm not going to actually do the calculation, I believe it came to be like 9.24 or something in that ballpark. It's a still fairly significant acceleration, even when you're out there, quote, weightless. We say you're weightless because you're in free fall. But you do still have a force of gravity. Okay, 2 clicker questions to get us started. These are clicker questions we ended with at my last meaningful lecture, which was a week ago today. In which case is momentum conserved? Okay, everyone has answered. Excellent. 2 to 18. Okay, the vast majority said in both elastic and inelastic collisions. That's the correct answer. Jaron, why would that be the correct answer?
Because it is conserved in both.
Yeah, but why?
Because in both cases,
Chad, you're not helping.
I don't know what.
Okay, it's really important to understand why momentum is conserved in those, because momentum is not conserved in every situation, and these are situations where momentum is conserved. We had from Newton's second law, the change in momentum is equal to the net force multiplied by the time over which it acts. And so momentum is only conserved if this thing here is approximately 0. Now, it's generally not going to be 0, so this here is for momentum conservation. So the net force, when I say the net force, if I'm talking about the net forces acting on Chad, I'm not going to include internal forces. I'm not going to include the force of the ankle bone connected to the leg bone. I'm not going to include internal forces. I'm only going to look at the external forces. So the net force is only looking at the external forces because the internal ones add up to 0. So if the net external force is 0, now during a collision, like in 2 slides, I'm going to bring up a problem with a collision. During a collision, you have 2 cars hitting each other. If the cars are not on ice, remember that's our physics term for saying there's no friction, then there's going to be a frictional force. But that frictional force is small compared to the forces involved in the collision. And furthermore, the time of the collision is very short. And so because it's very short for the collision, and generally the external forces are small compared to the internal forces, then this is approximately 0 and momentum's conserved in a collision. So that's only during the time of the collision, not from before, not from 10 seconds before to 10 seconds after, just during the time of the collision. Okay, next question. In which case is kinetic energy conserved? Okay. This time we had 21,100. Only inelastic collisions. That's right. That's the definition of elastic. It's the collisions where kinetic energy is conserved. So there's no other explanation except for that's the definition. Okay, so let's look at a problem. So here is a typical real-life problem. I was just yesterday looking at one of the job applicants, and he has a blog, and he says, we need to make sure our problems are actually meaningful real-life problems. not contrived problems. He showed an example of a problem that we do in calculus all the time, but it's rather contrived. This one here is very much real life. If you've ever seen a car accident, you know that the law officers, when they show up, bring out that little wheel and they measure the lengths of skids. Do you know why they measure the length of the skids? They do it so they can reconstruct and determine how fast you're going. I'm pretty sure I mentioned this like 2 weeks ago, but that's a very important part of reconstruction. And so I went and looked, and you can find all kinds of pictures where they show you the skids and show you, then they use computer models to first graph all the skids, and then they calculate how much energy was involved, and all the way through. They're doing all physics that we can do right now. You have these people who make their living being expert witnesses on collisions, and they're using physics at the level that you can do now. They practice it a lot, so they probably do it faster than you do, but it's nothing you can't do. It kind of makes you sad when you have people who make their living doing stuff that's really easy. So, and right now it's not easy to you, but it is if you've done it for a year. So I put here information. Car 1 with mass of 1,500 kilograms is driving down the road at 25 meters per second, which is 56 miles an hour roughly. Basically doing the speed limit until they got rid of the double nickel. Car 2 with a mass of 3,500 kilograms is speeding, coming from behind, hits the brakes and skids for 20 meters. Right, so you measure, skid for 20 meters, they hit each other, and then after they hit each other, they stay together and skid for another 150 meters. How fast was car 1 traveling before he hit the brakes if the coefficient of kinetic friction was 0.334? That's the real life problem. They want to determine, was he going at some crazy speed, or how much money should we fine him is generally the calculation here. Everybody understand the problem?
You mean car 2, right?
How fast was... Oh, yes, I do. When I wrote this, I put car 1 and car 2 opposite of what I usually do, and then tried to remember what I'd done. So first thing I did was draw a little figure. This is my very best artwork. I had car 2 coming along, skids into car 1, and then the two slide together. Tried to show them sliding together there. So I've got it laid out with my information there. I have the initial speed and the... Well, I don't have the masses written down. The distance is written down. Now I need to work on how am I going to solve this to find out how fast car 2 is traveling before it hits. So physics is about understanding how things fit together. So when you look at this, you're trying to figure out how things fit together. Let's talk about kinetic energy. I won't talk about potential energy because you don't really have anything here. Work and momentum as we go along. So initially we had two cars traveling with some kinetic energy. One of them hits the brakes. So let's focus on that one. When he hits the brakes, in terms of energy or momentum, what's happening?
Friction is doing work to remove kinetic energy.
Okay, friction is doing work to remove kinetic energy. So we can relate the speed that he had when he hit the car to the speed he had when he hit the brakes, using the work-energy relation there, because we have the work done by friction is going to be the change in kinetic energy. Then we have the collision between the two. What kind of collision is it? It's inelastic. So in an inelastic collision, and completely inelastic, or as our textbook calls it, perfectly inelastic, they stick together. So we don't have conservation of kinetic energy, but what do we have conserved? Momentum. So we can use conservation of momentum along with the fact that they stuck together so they have the final speeds to relate the two speeds before the collision to the one speed after. Then after the collision, what's going on? Friction is doing work to remove all the kinetic energy. So we're back to a work energy problem for after the collision. Now we're trying to find the beginning situation, so where do you suppose we should start? At the end. So we'll start at the end. and use the work energy relation to find the speed just after the collision. That's a FIND. Once we have the speed just after the collision, we're going to have to use our conservation of momentum to find the speeds before the collision. So use conservation of momentum. So that was 1, 2. That's a C. And what will our final step be?
Velocity of the car before it gets brake, right?
That's what we're looking to find, yes.
We're gonna do this one.
So the final will be to use work energy again. So now we put that into practice. Right? This is, most of our physics is done. We figured out what's going on, how it fits together. Now we just have to identify what equations go with this and how to put them in. That is not good. I noticed it was looking funny before. It's actually never done this to me using the Chromecast. Did that using Miracast a lot. I'm just going to change to the hard wire because, that's kind of useless, right? That's not the way it's supposed to be. Okay, looks better. Okay, so doing step 1, I'm going to have work non-conservative is equal to change in kinetic energy plus change in potential energy. What's the kinetic energy here? When they come to rest, what's the kinetic energy? 0, right. The kinetic energy right after the collision. What would the kinetic energy be right after the collision? We don't have a number for it, but we can write an equation, right? It's going to be 1/2. Both cars have the same speed, so I'll combine them together and just say mass 1 plus mass 2 times v, and I'm calling it y squared. What about the kinetic energy? Well, actually, that's all I care about right now. Potential energy. What can you tell me about potential energy? Haley, I saw you make an indication you know.
There is none.
There is no change in potential energy, so I might as well just set it equal to 0. As I was saying to Michael this morning, we could set it equal to, any random number, 5.269 times 10 to the 7, and we just have that in each step, and it still makes no difference. So 0 is the easier number. So I'm just going to put potential energy equals 0 throughout, so I don't have to worry about it. Okay, so we have our energy stuff, but we are using the work energy relation. I need to know the work. What would be doing work on these two cars as they're sliding? Okay? Work is done by friction. If I draw my two cars, there they are, and draw a free body diagram for the two cars, I have the force of gravity down, the force normal up, the force of friction going to the left, and of course they were sliding to the right. Actually, I'll put D there. Sliding to the right. So if you look at this, it was correctly identified. It's the force of friction that's going to do work. Force of friction is to the left. The distance is to the right. What does that tell you about the work non-conservative, the work done by friction? It's going to be negative. So I'm going to have work non-conservative is equal to minus the force of friction multiplied by the distance it slides, distance 2. Well, what's the force of friction? Force of friction is mu times the force normal. In this case, if you look in the vertical direction, you have only 2 forces. Sum of the forces in the y direction equals mass times acceleration in the y direction. It's not accelerating in the y direction, so that's 0. Force normal minus force of gravity equals 0. And you get force normal is equal to the force of gravity is equal to mg. Now, which m is this? It's the mass of both cars because they're both sliding together. So this mass is the combined masses. I should be careful and put m1 plus m2 g. So that means my work non-conservative is equal to minus m1 plus m2 g mu sub k d2. That's my work. The work-energy relation says that's equal to change in kinetic energy plus change in potential energy. Potential energy has no change. And so I have kinetic energy final was 0. And I'm ending up with minus m1 plus m2 g mu sub k d2 equals 1/2 m1 plus m2 vy squared. So it's not so hard. I can solve that for vy. I'll have to multiply both sides by 2. I forgot the minus sign. See that minus sign right there? That needs to be here. I can cancel the minuses, divide by m1 plus m2, which is going to get rid of that. And I will have Vy is equal to the square root of 2g mu sub k d2. This should look familiar, Michael, because we basically did this for a different problem this morning, right? So now I'll go ahead and calculate that value just to find out how fast they were going after the collision. It'll come up. D2 And so some of you have calculators there. What do I get from that calculation? Now remember, car 1 was traveling 25 meters per second before the collision. Car 1 sped up from 25 to 31.3 meters per second. Person in car 1 was sitting here, got hit and went, because that would be a very rapid acceleration, and their head, unless they have the seat back set right, because of inertia, is going to fall back as the rest of the body is pushed forward. That's why it's actually important to have your seat belts up so that they're at the back of your head. When I was in the fire department, our captain, who is now like either second commander or commander of California Highway Patrol now, he laughed about people who put their headrests down here at their neck, called them neck breakers. Because if you have your headrest set down here, which I know for short people it's probably not a problem, but for tall people it's common. If you get in an accident, instead of helping protect you, it's just going to snap your neck and make sure that it's fatal. You want to make sure that that headrest comes up to support your head so it can't snap back. Okay, so we've done step 1. On to step 2. Step 2 was analyzing the collision. So for step 2, I had momentum conserved, so I'll have the speed of car 2. I'm going to put speed of car 2 prime to be the speed of car 2 just before the collision, multiplied by the mass of car 2, plus the speed of car 1 times the mass of car 1 is equal to the combined masses times the speed y. Why did I do that? This was the momentum before the collision, the momentum after the collision. And somebody might say, wait a minute, that's not the initial momentum, because the problem didn't start with that momentum. Momentum is only conserved during the collision. So I didn't start the beginning of the problem for momentum. I started the instant before the collision. So I had the two cars, they're together, had the final. So I'm trying to solve for the speed of this one. I know this already. I just calculated that. So V2 prime is equal to M1 plus M2 Vy minus V1 mass 1, all divided by mass 2, which means I'm going to have 1500 plus 3500, those are kilograms, minus and I have V2 prime, the speed at which car 2 was traveling just prior to hitting car 1. What do I get?
34.
And by I mean you. 34 point what?
0.
Okay. So we have 34.0 meters per second is the speed that the truck had. I say a truck because it's a pretty heavy car. After skidding to, for what, 20 meters before hitting the car? Was it 20? Does anybody remember? It was 20? Okay. So now we're ready to go on to step 3. Use once again the work-energy relation to find how fast the truck was traveling before he hit his brakes. So just as before, the work non-conservative is equal to minus the force of friction times distance 1 minus the force of friction mu kinetic times the mass of just car 2, because that's the only one skidding in the beginning part, G, D1. Well, change kinetic energy, I'm not going to go back because it's going to take an extra 5 or 10 seconds to go back and come forward. But we had the kinetic energy that it started with, 1/2 m2 v2 squared. We're looking for that v2. And the kinetic energy x, the kinetic energy just before the collision, would be equal to 1/2 m2 v2 prime quantity squared, where we've just calculated v2 prime. So using my work energy relation, yeah, that works fine for me. And so if I want to solve for V2, I have to first multiply both sides by 2, divide by M2. So I did the division, so I'll have these cancel, Notice this M2 cancels with that M2. And then I have V2 prime and V2. I forgot the square there. So I'm going to have to rearrange this to have if I want to solve for this one, I'll move it over here, move that over there, and square root. V2 is equal to the square root of V2 prime quantity squared plus 2 mu k g d1 equals the square root of 4.0 meters per second quantity squared. And so what do I get for the beginning speed of the truck? Either this 20 is wrong or you did it wrong, because it comes out to be, I think it's 39.4 or something like that.
I got 35.9.
You got 35.9 as well?
Yeah, those numbers.
Then maybe the distance wasn't 20 initially. I'll go back and check. Yeah, well, I'm pretty sure that the 34 was correct as well. I am not not sure how this failed because I did it before class to make sure I would know the answer. It comes out to be he's traveling a little over 88 miles per hour. Right? I made it realistic. And yeah, there shouldn't be any problems with this equation, but I can't tell you what's going wrong. So everybody's getting a very consistent 35.8. Well, I'll sit down afterward and see where I made a mistake in this last part. Or maybe I put the equations wrong in the spreadsheet. That's always an option. Yeah. It's always a downer to get to the end and think I have it wrong. I could pretend I thought that was the right answer, but I don't think it was. Why did I do this problem? Not to embarrass myself. I did to illustrate, once again, how to solve a collision problem and how this is used in real life. How this kind of information, being able to relate the momentum and energy through collisions, is useful. Moving on, two-dimensional collisions. I will not ask you any questions about two-dimensional collisions. If you know how to do a one-dimensional collision, you fundamentally know how to do a two-dimensional collision. All that's different is conservation momentum, instead of being just one dimension, you have two dimensions. So you have two conservation momentum equations. Set your coordinate directions. Pretty much you always set your coordinate directions so the initial momentum is parallel to one of them. And your momentum in the x direction remains constant. Your momentum in the y direction remains constant. So you just have two conservation momentum equations. Kinetic energy is a scalar rather than a vector. The big reason why energy is easier for many cases to solve problems is because it's a scalar rather than a vector. You don't have to worry about direction. But that means in a two-dimensional collision, you still only have one conservation of kinetic energy equation if it's elastic. You don't get two because it's not a vector equation, it's a scalar equation. I will point out one thing that is unique and interesting, especially if you play billiards or pool or something. If you have two balls of identical mass and they collide, you either have to have the two balls going in the same direction, which would be a one-dimensional collision, or one ball stopped, or the balls are going away from each other at a 90-degree angle. Now that's a special case if the two balls have the same mass. But if you're playing pool, that's kind of important. You look and you're like, ooh, I could hit this ball and go into the corner pocket. Where's the cue ball going to go? Well, you can just sit there and say, okay, so the ball's here. The ball's here. It's going to come in like this, and I want this one to go, well, that's the wrong one. I want this one to go this way. Then you just draw the right angle. And this picture, I know that doesn't look like it's a right angle, especially the way I drew it. But this should always be a right angle if they are equal mass balls. And so you can figure out what direction the ball is going to go. Now, if you're good at pool, you can go a step further. You can put spin on the ball that will alter that a little. We're treating these as point masses with no spin effects because that increases the complexity quite a bit. So pool does have more complexity than just this basic treatment because you have the balls spinning. But if you were playing pool with no friction involved, so the spin didn't matter, like your ice pool table, then that'd be perfectly correct. Okay, so that's all we're going to have about two-dimensional collisions. Just need to know that you do have momentum conserved in all of the dimensions of the collision. But kinetic energy, if it's elastic, is still just a single equation. It's not a vector equation. Next, we have 3 slides on rocketry. How does a rocket work? This is one of the classics. Published in 1969 in the New York Times was this correction. That on January 13, 1920, they had an editorial written by the editor of the New York Times that said in part, and you can read the quote there, Professor Goddard, with his, quote, chair, end quote, in Clark College and the countenancing of the Smithsonian Institution, does not know the relation of action to reaction and of the need to have something better than a vacuum against which to react. To say that would be absurd. Of course, he only seems to lack the knowledge ladled out daily in high schools. Now, we're a college, we're very small cut above what's ladled out in high school physics and in this level of physics class, but we are cut above. Don't want you to think, I said teaching high school. If you want a high school equivalent class, you take Physics 111. So, he was clearly wrong. We send rockets into space all the time. What's going on? Why did they have to print this retraction, about 48 and a half years after publishing it? Of course, they could have printed it much earlier, but what's going on with the rocket? What was the editor thinking was going on with the rocket?
It was pushing against the air and the air was separating.
Yeah, it was pushing against the air. So he was thinking of it much like the air is the floor. And so I can stand on the floor and I go like this, and I leave the floor for, 10th of a second, because I've got mad hops. I had to push against something. If I wasn't on the floor, like let's say that I was lying on the bed and I just kicked against nothing, I wouldn't do anything. Right? I have to have something to push against. And that's what he was thinking. That the rocket won't work because you're ejecting material, but it has nothing to hit, and so it'll just go out there. And what he was thinking was, sure, on Earth where we have atmosphere, you eject material from the rocket, it hits the atmosphere, and then it pushes back. But in space, there's no atmosphere. You just push it out, there's nothing there. What the editor was missing was the basic idea. Well, I like to think of this as simply a conservation of momentum. If you have a rocket that has fuel, think of the case, you'll be the rocket, you'll be sitting on an icy lake, and all you have is your backpack. That's your fuel, the backpack. You're initially at rest. If you throw the backpack that direction, what's going to happen to you? You're going to go that direction because the net force on you is zero, right? There's no friction, icy, right? So if the net force on you is zero, momentum is conserved. The backpack went from stationary going that way. You had to go from stationary to going that way. So the total momentum remained zero. And that's what's going on with the rocket. With the rocket, you have fuel in the rocket. The rocket burns the fuel, and ideally that fuel all comes out going the opposite direction you want the rocket to accelerate. And so that fuel went from going the speed of the rocket to traveling away from the rocket with a speed, we call it the expel velocity, the velocity of the expelled fuel, that relative to the rocket is going away. And so the speed of that fuel went from the speed of the rocket to the speed of the rocket minus v sub e. Well, for conservation of momentum, the rocket had to pick up speed. The rocket also has less mass in it, by the way, because it expelled mass with velocity. So it becomes a calculus problem. Well, we're not the calculus class here. We've already done this problem with the calculus class. So I'm just going to two important results. The first one really is a calculus result, but as the people in calculus will know, used deltas instead of d's to make it so it fits in with an algebra. The acceleration of the rocket, if you're dealing with the Earth's gravity and you're going upward, then your acceleration is going to be the acceleration you get from the thrust, the velocity at which you're expelling the fuel, divided by the total mass of the rocket, times that delta m over delta t. That's the rate at which you're burning the fuel. So the important things for the acceleration are the burn rate, which they just use capital R for the burn rate, and the velocity of the ejected material, and the mass of the rocket. Obviously, if you have a less massive rocket, you'll have a bigger acceleration for the same amount of the other two. And that minus g is just because if you're in the Earth's gravitational field. When they actually shoot off the rockets, they lay them out on their backs, and they fly in the direction that the Earth is rotating so they can pick up some of the Earth's rotational energy along the way. And we generally don't worry too much about this because the thrust is a lot bigger than g. Well, hopefully it's a lot bigger than g. I shouldn't say it's a lot bigger than g so many times it's smaller than g. General physics class, we don't worry about it though. This second equation is an equation where we didn't worry about g. We said, okay, if we had this rocket going and there was no gravity, what would its final speed be after it burned all of its fuel? And this equation here tells you how fast the rocket would be going. It's the speed at which it's ejecting the fuel times the natural log of the mass you started with divided by the mass you ended with. So the key to that is the greater percentage of the rocket that is fuel, the faster it's going to be. So you had a problem or you may have had a problem in your reading quiz that looked at a problem in the textbook, calculating that if you ignored the gravity and atmosphere, you would have to have 98.9% of the mass of a rocket is fuel for a rocket to escape from the Earth. And that's the ideal situation. The more realistic situation was, 180 times, right? Fraction was like 1 to 180 for the mass of the rocket compared to the mass of the fuel. Enormous amount of fuel necessary for a rocket to escape. Well, some of the things they do to allow themselves to still launch rockets that have some reasonable payload is to have things like staged rockets. So in the space shuttle, you had these two rockets on the sides and this big fuel tank in the middle, and those would burn initially, get it up to higher atmosphere, and then you just eject the tanks and the rockets. And so you drop off a lot of mass, and then you have the fuel that's in the space shuttle that then is burned after that to keep it going. But by dropping off some of that mass, you can increase your speed by lowering the mass of the rocket. So that's why they use staged rockets, so they can drop off unneeded mass and get the higher speeds available. Okay, I only have 2 slides left. I have 5 minutes. That's actually not bad timing, except for I have a lot of material I want to talk about in these 2 slides. So, equilibrium. This is now chapter 9. Equilibrium, the word itself, equa means the same. Librium is force. So equilibrium, technically that would just be equal forces. Now, in practice, equilibrium is something different than that. Equilibrium has two pieces to it. Rule number one, the first condition of equilibrium is the net force equals 0. Now, if the net force is 0, what does that tell you about motion?
Should be constant or none.
It's going to be constant. It can be moving, but it has to be moving with constant velocity. So if it changes direction, that's not constant velocity. If it changes speed, that's not constant velocity. But if it's going at constant velocity, constant speed and direction, that's still an equilibrium situation. We often like to talk about static equilibrium, which is stationary equilibrium where the velocity is 0. But that's static equilibrium. Equilibrium general doesn't have to be 0. The second condition is that the net torque has to be 0. Well, clearly I have some explaining to do because we haven't talked about torque whatsoever here. So let me start with the first condition and then get to the second condition. The first condition is simple. If the net force is 0, you're in equilibrium. Newton's second law says the net force is equal to mass times acceleration. So if the net force is 0, you have no acceleration. That's another way of then describing equilibrium is no acceleration. It's not the technical way of describing it, but it's an equivalent way. So if I'm standing here right now, as that picture shows, I'm in equilibrium because I'm not accelerating. The net force is on me. I have force of gravity down, force normal up. They're adding up to 0. Now, I can do things that will make me unstable. Like if I lean over, I could start to fall, right? If I'm starting to fall, I'm accelerating, which means I'm not in equilibrium. So how is it that leaning over is going to make me not in equilibrium? That comes to the second one, torque. Now, when I was a young one, like let's say 8 or so years old, my dad and my Uncle Jack, not the famous Jack Webb, were talking about cars, and my dad said, yeah, that thing's got a lot of torque. And I piped in, Daddy, what's torque? And my dad thinks for a second, he says, well, it's kind of like the amount of twist the engine produces. And like any intelligent little 8-year-old, I said, okay, Dad doesn't know what torque is, and dropped it, right? I figured he'd just give me a stupid answer. But it turned out it wasn't a stupid answer. My dad knew more than I gave him credit for. Torque is the rotational equivalent to force. So force pushes or pulls and makes things accelerate. Torque twists and makes things change their rate of rotation. So torque, and if you're an engineering student, which I believe I have a number of this year, engineering students talk about moments. You have the first moment, the second moment, and so on. I don't know which one it is, but torque is one of those moments. Torque is a result of force. You have to have a force to create a torque. So the picture on the right here illustrates a situation where the forces are equal. You have, this is supposed to be a hockey stick. I assume it's supposed to be a really lame goalie stick that's lying flat on the ice. And then you have two forces on it. We call it a couple, by the way, if those forces are equal, pushing different places. What's going to happen to that stick when you put those two forces like that? It's going to rotate. Or, you could break it if you do it really, really hard. Okay? But it's going to rotate. What could I do? How could I use the same forces and adjust it so it doesn't rotate? Okay, if I set them so they're pointing at each other, then it won't make it rotate. But if I put them offset, it'll make it rotate. So torque is a twisting force. There must be something about where you place the forces that affects the torque. And in fact, it turns out it's a simple equation if you know your vector algebra. I have a question and then that picture, and then we'll, now you can answer. No one's answered yet, just in case anyone thinks they have. For this one, you have to answer all that you think are correct and then hit enter. Okay, we had 16, 0, 18, 5. These two were indeed correct. If the car is parked, its acceleration is 0. If the car is traveling on a straight freeway at constant speed, the acceleration is 0. If the car is rounding a corner at constant speed, what kind of acceleration does it have? Centripetal. It has acceleration toward the center, so that's not an equilibrium condition. And of course, accelerating, it's also accelerating. Okay, we're out of time, so I won't put any torque questions on the homework. That's the definition of torque.
So last night I went to look for the PHYS, and